Right. So last week, we talked about finite impulse response filters in BlueSpec, not just in BlueSpec, in general, how to implement this in hardware. Because, like you mentioned last lecture, if we try to implement something like this in a filter, in a kind of like how we do it in software by having a two-layer nested for loop, that will be very, very bad for performance, partially because the clock frequency of FPGAs is relatively low. So our design was to have, and this is going to be typical, this is the typical theme for all the designs that we do for FPGAs, is to have multiple multipliers and a tree of adders, so that we can have all these arithmetic units operating in parallel, implemented in the form of a filter, implemented in the form of a systolic array, so that data comes in without any blocking. Data is always just flowing in, one element per cycle. Results are always flowing out, one element per cycle. And we have enough processing units, multipliers, and adders to keep that flow going without any back pressure. And we showed, and we showed how that was done in BlueSpec. And we're going to move forward to look at a couple more examples, just to give sort of a feeling for how these kind of designs are done. Another example application is something I showed once in one of the previous slides, calculating gravitational force between two particles, x1, x2, located at x1, y1, and x2, y2, mass of m1, m2. This involves 8 instructions, 8 floating point instructions, subtraction, subtractions, multiplication, multiplication, addition, multiplication, multiplication, and then division. So 8 arithmetic operations. If we don't have superscalar, out of order, whatever, or SIMD, this would require 8 cycles. But anyways, per ALU on a general purpose processor, it's going to take 8 cycles to actually process this. So if we go that path, if you have a single stream, single thread processor, no SIMD, we're going to get one answer per 8 cycles, ignoring the overhead of the load store operations, ignoring the overhead of control flow operations like loops and things like that. And on an FPGA, we can implement this in the same way, using a systolic pipeline systolic array, just like how we did for the FIR filter. We can have a pipeline of the multiplier, the 2 multipliers, the subtractions, the squares, subtractions, and then the additions and the divisors and everything implemented in a pipeline format. So that any given time, once the pipeline fills up, at any given time, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 operations working in the pipeline at any given time. So with this design, we can get one answer per 1 cycle. And this is how something like a 200 megahertz FPGA can actually compete in performance with a 3 gigahertz processor. On top of that, this is a pretty simple systolic array. We can fit a lot of these into a chip, unlike cache coherent cores. Cache coherent x86 processors right now typically come with something like 4, 8 threads with hyperthreading, at least for desktop class stuff. Whereas FPGAs, a multiplier takes maybe 1 or 2 DSP blocks, and even the small FPGA I showed just now has something like over 100 DSP blocks. So we can fit a lot of these pipelines into even a relatively small, modestly sized FPGA. So we get, if you look at just the flop count or ops per second count, per ALU, you would get 1 op per cycle. But if you have a pipeline systolic array, you can get how many number of arithmetic units that you spawned per cycle. So if you have 8-stage pipelines, we can have 8 operations per cycle. So 8 operations working at a smaller clock, lower clock frequency can kind of compete with 1 operations per cycle running at a higher clock frequency. And because these things are simple, we can fit a lot of these into a chip. That's where the performance benefits come in. So Actually, pipelining the implementation can look a little bit like this. We have a pipeline of the multipliers, multiplier, multiplier, subtractor, subtractor, and squares and all that stuff. But the interesting caveat here is that we need to have, because we need to have a balanced pipeline. We're going to talk about what exactly that is and how we can reason about it in a bit. But if you remember the pipeline balancing issues from undergrad computer architecture, they should be fairly straightforward. Because the set of inputs that come in on this side needs to always progress at the same pace in a lockstep through the pipeline, we need a bunch of these pipeline registers in the middle to make sure that all of the computation between these numbers happen between the same set of numbers. For example, if we issue one set of computation, and then we issue another set of computation in the next cycle, because we want to calculate the gravitational force between two different pairs of particles. We don't want these parameters getting mixed up. So everything has to operate in lockstep and have pipeline register. This is pretty much the same thing that we did for pipelining at undergrad computer architecture levels. So in this implementation, you will have a computation will have a latency of 8 cycles, throughput of 1 cycle, a throughput of 1 result per cycle. So that's good. On the other hand, if we want to further pipeline, if we want to further parallelize the operations, we can do something like this. Instead of having a pipeline, so if you look at the previous example, we had an 8-depth pipeline, just conceptually organized into a chain like this. But since if we can actually reason a little bit more deeper about the dependencies between these computations, some of these, for example, all of these multiplications on the top can be done completely in parallel with all of these other operations in the bottom of the divisor. They don't necessarily have to wait in a pipeline, in a set of pipeline registers. So maybe what we can do is just have them work in parallel. In that case, the pipeline becomes much shorter. And at every pipeline stage, there's more operations. In the previous example, we had 1 arithmetic operation per pipeline stage, distributed across 8 pipeline stages. But now we have sometimes 3 arithmetic operations happening in a pipeline stage, distributed across only 4 stages. So in this implementation, the latency would be 4 cycles, half, throughput would be 1. The same as before. And does this matter? The question is, the latency might not matter too much. If this is a stream processing. If you're always working on batches, if you're working on 10,000 pairs at any given time, this reduction in latency is maybe not that important. But if later computation depends on earlier results, if there's a tight feedback loop, for example, if you're working on an accumulator and we have to have the output of the adder before we push in the next adder, next value to add, then something like this can become important. So this is 2 different ways to implement, 2 different instances of ways to implement this simple example in a sea of spectrums of different ways of implementing this. Another interesting question to ask here, especially if we start dealing with actual real-world implementations on chips, is right now, well, this pipeline is receiving 6 input elements, 6 numbers per cycle, excluding G, because G is just a gravitational constant. It can be, it's not part of the, I mean, it can be part of the input depending on how you want to design it, but it doesn't have to be part of the input. So M1, M2, X1, X2, Y1, Y2. So 6 input elements coming in per cycle, assuming 4-byte single precision floating point numbers, that would be 24 bytes of data coming in at every given cycle. And this might be fine. 24 bytes is a bit over, a bit less than 256 bits, which is typically okay if this data path exists entirely in silicon inside the FPGA. But if this FPGA is being plugged into a bus, for example, if this is plugged into a PCIe bus, if this is plugged into a AXI bus, maybe we'll have a chance to talk about AXI buses in a bit. Even if it's it can be plugged into an AXI bus, if it's plugged into UART, if it's plugged into a USB controller, the data path may have a fixed width that is smaller than 24 bytes. So the question becomes, if our pipeline input has 24 bytes width, then does our bus support it? This becomes an important problem. One thing we could do is simply just have a serializer here, deserializer here. Whatever data path comes in, it could be, I don't know, 4-byte data path, but maybe we can just scatter it as in a round robin fashion. Once data comes in, first cycle, we send it to M, the next cycle, we send it to M2, the next cycle, we send it to MX1, next cycle, send it to X2, etc., etc. We can do that. But if we do that, at every cycle, there will be some arithmetic operators that are not doing useful work, even assuming that we change the pipeline so that the pipeline is still balanced. In the first cycle, the multiplier is working, but the subtractors are not doing anything. The next cycle, the multiplier is already done, so the data has been moved on. The multiplier is not doing anything. The subtractor is now doing something, but the next subtractor is still not doing anything, so on and so on. So some of these devices, some of these arithmetic operators, if the data bus is too narrow, if the incoming data throughput is too small, too slow, then some of these arithmetic operators will be kind of sitting there idle, not doing anything important, just taking up chip space. And that might be okay if chip space isn't a critical component, critical factor of the design that you're doing right now. So there's a lot of freedom when you do FPGA design. But if it is, then you might want to do something different again. Something like this, perhaps. So this design assumes the data path can only take in 2 data elements per cycle. So 64 bits, 8 bytes for 2 4-byte stuff. Thankfully, because the subtractor and the squares for these 2 operations on the top is pretty uniform, they can be shared. So for x1 and y1 and y2 and x1 and x2, the subtraction and the squared works the same. But once the square operator is done, the data can either go into this pipeline register or this pipeline register in a round robin fashion, so that one cycle later, you can add these two things together to get the bottom part of the divisor. And because on the top part, we're all doing multiplications, we can have one multiplier. But first, on the first cycle, we multiply M1 and M2 together, push it into a pipeline register, loop back so that we multiply the results of that to the gravitational constant G. And 2 cycles later, we move the data to the divisor. And the important thing here is that even first of all, we reduce the resource utilization of the design. The second thing is now not all the data are moving forward in pipeline stages one stage per cycle. For example, if you look at the very first pair of data that comes in, y1 and y2, the first cycle subtraction, the next cycle squared, the third squared, and then we push it into this pipeline register. In the third cycle, it doesn't do anything, it just sits here. The control structure has to be constructed so that the data just sits here. Because in the third cycle, x1 and x2, the results of x1 and x2, we have to wait until it comes into this pipeline register on top. So that on the fourth cycle, we can add these 2 things together. So until this pipeline register becomes occupied for one cycle, this thing has to wait. Similarly, until this pipeline process completely finishes, this pipeline stage has to wait. So there has to be a correct number of pipeline registers here to match the latency. But thankfully, because there's also a loop here, and M1 and M2 are the last to come into the pipeline. So 2 cycles later, only then these pairs of data will come into the pipeline, so that the number of pipeline registers required is still kind of small, just 1 actually. So interestingly, in this design, latency is 5 cycles, so slightly larger than the short latency implementation. But now the throughput became a third because we're not getting one output result per cycle, because it takes 3 cycles, 1, 2, 3, to in-queue the this one set of input data for the operation. We take 3 cycles to actually push it in. So only after 3 cycles, so every 3 cycles, we will get one result out. So this is an interesting balance, but I guess this is this reduction in throughput is something that we really have no way around unless we do something sideband like compression or something like that, because the bottom line is that we do need all of these 6 numbers to actually get a piece of result out. But if the data path is only 8 bytes in size, and it does require unchangeably, if it requires 3 cycles to get the entire set of inputs, then we can't have the output data coming out at every cycle. It will only come out, one output will come out every 3 cycles. And this, there's a little bit more elegant way to reason about this, the data path width and stuff like that, called the roofline analysis, and that will come up in a couple of slides as well. But right now, I'm not going to make you do these kind of designs for Lab 2 because we only have a couple of weeks. But I just wanted to show this to kind of put all these ideas into the back of your head, so that if you actually have to do this in the future, you kind of know what to look for. Yeah, an important aside here is a thing called Little's Law. Little's Law is one of the, I think at least, one of the few laws that we have to deal with in systems architecture and computer architecture. That's why I'm quite fond of this equation. I really want to either put this on the course website, the group website, or I don't know, even tattoo it on myself or something. The law itself is very, very simple. L equals lambda W, and L being the number of requests in the system, lambda being the throughput, W being the latency. So the equation is very, very simple. Given a system with W latency, and the system is capable of processing lambda throughput, the total number of requests that are being actively processed in the system is lambda multiplied by W. And if you turn it around, another simple analysis is if we have a system with latency W, if we want to achieve a certain amount of throughput, we need to be processing at least L things at once. A simple way to reason about this could be if we have a component in the system that can process up a set of input every 16 cycles, then if we want to get peak performance, 1 element per cycle output, 1 result per cycle output, we need to either replicate this processing module 16 times in order to process the 16 sets of inputs at once. Or maybe if the 16 cycle latency is completely pipelined, so that inside the pipeline there will always be 16 sets of inputs being processed, then that's one way we can get peak throughput. And we can see examples. An example of this is floating point arithmetic in FPGAs, and this is something that you will have to deal with Lab 2 as well. Floating point operations implemented using just lookup tables and CLBs is kind of inefficient. If you remember, CLBs is the configurable logic blocks, which is the basic unit of reconfiguration. It's inefficient because implementing multipliers also, I mean, for floating point operations, you do need to have multiples of multipliers and adders and things like that to support, single precision, double precision floating point numbers. So implementing all of that in CLBs is not necessarily very efficient. And if it's something that's used rarely enough, then that's fine. But since arithmetic operations are typically used fairly often if you want to do computation acceleration in FPGAs, Xilinx, and also I say Xilinx here, but also like Intel, Lattice, everyone provides configurable floating point cores, hard cores, which uses the DSP blocks, the ASIC shards inside the FPGAs, which actually implement the arithmetic units in ASICs and non-reconfigurable ASICs. Yeah, so it uses DSP blocks to implement floating point operators, and they do have variable cycles of latency. So it can be configured to have different latencies, but they're all completely pipelined. You can always push in one operation per cycle. You will always get one result out per cycle, but you can configure the pipeline depth of this operator. So if you have configured to have a very deep pipeline, it can achieve very high clock frequencies. If you configure it to have a very shallow pipeline, it will have a lower reachable clock frequency. And it can be configured to do either addition, subtraction, multiplication, division, sine, cosine, square root, things like that. It can also be configured to have variable bit width. It can be single precision, double precision. It can be whichever. You can make floating point multipliers of 17 bits wide. That's one of the strengths of FPGAs. It can optimize to fine-grained optimization for your applications. Anyways, but one example, at least for the Xilinx implementation, is that a single precision floating point number, so 32 bits, can have 7 cycles of latency if you want to achieve peak clock frequency. If you want to have a deep pipeline to achieve higher clock frequencies, because higher clock frequencies often translate to higher performance, the single precision floating point multiplier module can have seven cycles of latency if you want it to go as fast as possible. You can configure it to have lower cycles of latency. You can have it implemented in 2 pipeline stages, 3 pipeline stages, whatever. But your clock frequency, your attainable clock frequency will be slower if you go down that path. So what does that mean for our designs? Let's say we have a very simple example here. We want to multiply 3 numbers together. If we want to completely pipeline this implementation, I mean, we can always have one multiplier, and then we can do a multiplied by b first, and then when the results come out 7 cycles later, we can do that, multiply that against c. That's fine. We can do that too. But say we want to achieve absolute wire rate performance. We want to use 2 multipliers. If the example becomes more complex, if we start having more multipliers, and if you want to achieve high performance, you will want to spawn multiple multipliers, because that's where the strength of FPGAs are. So let's say we use 2 multiplier cores. Each of these will have a latency of 7 cycles, which means maybe looking at this example would be better. Which means if we push multiplication of A and B into the multiplier unit, 7 cycles later, the results of that will come out, which we can actually feed into the next multiplier to multiply that result against C. But because this multiplier is pipelined, we also need to balance the pipeline on the path for C, so that the set, this A, B, C set, the 3 numbers that belong to the same set of requests can be batched together into this new multiplier. So the C's path also needs to be forwarded via 7 pipeline stages. We'll show how to do this in BlueSpec. It's actually fairly simple to do this in BlueSpec to get maximum performance. What happens if the path for C has less than 7 forwarding stages? That's an interesting question, right? And that's where the little sloth stuff come in. Say we only have 4 pipeline stages on C's path side, but 4 pipeline stages on C's path side, Of course, if we do that naively, the pipeline depth on this path and this path will no longer be matched. So we will get wrong results. But say we took care of all of that already. Say if we only have 4 pipeline stages on C's path, but once we fill the 4 pipeline stages, we're not going to take, the circuit is constructed such that it blocks, it doesn't take any more input until the first output of this multiplier comes out so that we can evict one value from the 4 pipeline stages that we have, so on and so on. That will be correct, that implementation will be correct, but the performance will suffer if the pipeline stages here are mismatched, because the total number of elements we can have processing at any given cycle is only 4, even though this pipeline implementation of the multiplier can have 7 operations, 7 multiplications operating in parallel at different stages of the pipeline. If the number of pipeline stages that exists on this side is still is only 4, then the circuit will block after filling in this 4 registers. And even though this pipeline, the lower pipeline, can take up to 7 requests, it will only be filled with 4. So only 4 sets of inputs can be processing at any given time. So L equals 4, but the latency is still 7 because it takes 7 cycles for the output to come out. So the throughput becomes 4 divided by 7, which is 4/7. It's not 1 anymore. It is lower than 1. So that's where the Little's law analysis comes in. It's at least at our level right now, it's not very often that you actually have to do this analysis. This example is just given to kind of show the impact of having imbalanced pipelines. In our example, in our level, most of the times what we'll try to do is just have balanced pipelines. Yeah. So in order to actually do that in a simple way, without having to actually create 7 pipeline registers by hand, we can actually, inside at least BlueSpec, we can abstract the forwarding stages using a FIFO. So here we have mult1 and mult2, mult1 for multiplying A and B, mult2 for multiplying C. So let's say we have 3 values coming in at every cycle from the input queue. And for the multiplier 1, we can add we can put the A value and the B value, tuple 1 of A, tuple 2 of B, A and B. And meanwhile, C also has to be forwarded through its own path with pipeline registers. But we implement this queue, we implement that set of pipeline registers using a FIFO of size 7. So this is a very simple way of concise way of expressing the bypassing set of pipeline registers. And at the next rule, we can get the results out from the multiplier, and we can get the corresponding C value out from the C queue, and then we can start the next set of multipliers, multiplication. And then finally, we can get the results out and we push it into the result output. This way, everything is completely pipelined. Step 1, 2, and 3 will always be firing at any given cycle, as long as data is always there and the output queue is always has space available. So yeah, we'll be doing two floating point operations per cycle. So that's good. And what's good here, another good thing here is that FIFO length doesn't have to exactly match the latency. It only has to be larger than the other path. So if the FIFO size is 8, that's fine, it'll still work. If it's 10, it'll still work. It'll still be completely full performance, accurate processing, because this isn't a fixed, yeah, I don't need to talk about that, but yeah, it will still work. If the FIFO size is smaller, it'll still work. It'll still be correct, because the circuit blocking, managing the number of elements inside the bypass queue, all that stuff is handled by the language automatically. so that if the FIFO size is 2, for example, once the CQ is filled with 2 elements, CQ.InQ will block, turning it into a implicit guard for step 1, which prevents more than 2 requests to be in flight at any given time. So all of that is handled automatically. So that's the big benefit of using a high-level language like this one. Another example, the same example is memory and network access latency. I won't go into too much details about this one, but the latency that we deal with in this kind of situations is much larger than just having one floating point operator. Assuming a 2 microsecond network line round trip latency, 2 microsecond is fairly low, but at 2 microsecond round trip latency, the FPGA running at 200 megahertz, network latency is 100 cycles. So if we do a read request over the network, Little's law means that 100 requests must be handled in flight to maintain full bandwidth, meaning the forwarding pipeline should also have more than 100 stages. We're going to talk about why in a bit, but a pipeline, a FIFO with 100 stages is fairly difficult to fit on chip, so we'll have to use something different, but we'll talk about that later. Yes. Again, since in the interest of time, we won't go into too much details about this one. For at least for the purpose of lab 2, we won't have to care about this one too much. But yeah, if some pipeline stages, if some pipeline implementations that you have to do may inherently have high latency, but also cannot handle many requests in flight at once. For example, the GCD module can only have one input set being processed at any given time, if you remember. So it has a large latency, especially if the input value is large, but the number of elements that can be processed at any given time is just 1 for the GCD module example that we showed. So for this, in order to increase L, increase the number of elements that is being processed at a given time, we need to replicate the high latency pipeline. We need to replicate the high latency processing module. So we have to have a lot of those things. And for all the inputs that come in, we either distribute it across the modules in multiple ways to handle this. We can distribute it across the modules in a round robin fashion if the latency is kind of fixed, but if the latency is very variable, then you might want to have a signaling mechanism so that each module, when they're done, maybe they can push a token into the system to say that I'm ready to do the next piece of work. Anyways. Yeah, I forgot. In the interest of time, let's see, should I talk about this? Yeah, this is the same topic that was kind of briefly mentioned in the gravitational force pipeline with the data path width. So in the simple floating point multiplication example, A multiplied by B multiplied by C, if we can push data into the system at 12 bytes per cycle, then we get maximum performance at 200 megahertz. 12 bytes being processed per cycle would be 2.4 gigabytes per second. So the fully pipeline implementation can consume data at 2.4 gigabytes per second. If we're getting less than this, then there's a bottleneck in computation. So when you run the simulation, you know that the data is being fed into the system at 12 bytes per cycle, but we're not getting 2.4 gigabytes per second, that you will know that there is a bottleneck inside the computation. Could be some scheduling issue or some other pipeline mismatch issue, whatever, that you have to fix. But the question becomes, what if you want more than 1 tuple per cycle? Of course, we can replicate the whole pipeline multiple times, but there's a different way of doing this as well. We can increase the width of the data path. In the previous example, we dealt with the problem where the data path was too small. But if for example, if we're dealing with the pipeline inside the chip itself, where we have a little bit more freedom in terms of the width of the data path, what we can do is increase the width of the data path to have more sets of inputs coming in per cycle, so that we can have, and if the processing can handle it, and the performance will be higher. If you have 8 bytes coming in per cycle running at 200 megahertz, that's 1.6 gigabytes per second. But if we can have a much wider data path coming in, more data elements coming in per cycle, and if the processing is parallel or can handle this in other ways, then 32 bytes coming in per cycle running at 200 megahertz would be 6.4 gigabytes per second. So a much higher performance. And the processing will also be modified, needs to be modified to handle this, either by replication, algorithmic redesign, or pipelining, and so on and so on. Of course, there's multiple different dimensions on how to, orthogonal dimensions on how to deal with this. One other thing we could do is just make the clock go faster. If the clock is 400 megahertz, then the performance would be 3.2 gigabytes per second. But oftentimes, because of the complexities of the circuits that we build, sometimes we can't make the clock's frequency go fast forever, as is the inherent problem with modern CPUs. So these other tricks need to be played. And this is where the issue of importance of the roofline model comes in. So the roofline model is, if you're, some of you may be familiar with this already, but the roofline model is a performance model. It's a very, very simple performance model, modeling the attainable performance of a simple system with memory and processing. And because computation is typically, and we intuitively know this already by dealing with things like matrix multiplication and things like that. Performance is, most of the times, performance is either bottlenecked by processing or it's bottlenecked by accessing memory. It's typically one of two things. Meaning, as compute intensity, meaning computation per memory access, how much computation do we do per 1 byte of memory that we load from memory? As computation intensity increases, given a fixed computation performance of the machine, the bottleneck moves away from memory bandwidth to computation performance. Say we have a fixed computational throughput. If we load a lot of memory and don't do too much computation on each byte of memory that we load, then in order to keep the computation unit busy, memory has to be faster. On the other hand, for every little bit of memory that we load, if we have to do a lot of computation, given a fixed computational budget, the performance bottleneck will typically move to the computation unit. And this is important not just for FPGAs, it's a good way to determine the kind of performance we should be getting in a given system. So it looks like this. Given a fixed computational performance, computation budget, as the operational intensity increases, so more computation per memory load, if we have a very large operational intensity, a lot of computation per every bit of data loaded, then we would have hit the peak performance of the computation unit, of the CPU, of the FPGA, whichever. But if the data is more memory access dependent, then the performance will be bottlenecked by memory performance. As the memory becomes, as the memory as the computational intensity increases and the memory performance is kind of fixed as well. As the computational intensity increases, more data computation to be done per every bit of data that comes in, then the computation can always keep up with that data rate, meaning the performance actually increases as the computational intensity increases. Another way to reason about this roofline model is considering the x-axis as the computational performance. If you consider the x-axis as computational performance of the computation unit, and y-axis is as the actual attainable computation, as the performance of the CPU or the FPGA increases, we will get higher performance, but at some point we will reach the memory bottleneck. At which point it doesn't matter if you have higher performance, you will be bottlenecked by the memory. So that's another way of looking at this chart. Of course, the labels have to change, so it's not we're not looking at the same chart, but that's one way the roofline model is actually expressed as well. Yeah. So of course, we don't want the computation implementation to be the bottleneck. If you're doing FPGA design, we don't want the FPGA core to be the bottleneck. So our goal is to either saturate the PCIe, saturate the network, saturate the DRAM, et cetera, et cetera. Yeah, we won't talk about the delta compression because it's going to take too long. And now we finally get to go to the second part of FPGA accelerator design principles, which is timing issues. Timing issues drive the clock frequency that your FPGA design can reach. And before we get there, this is an interesting chart from Xilinx comparing the performance of a neural network inference implementation on FPGAs, GPUs, and CPUs. So the blue lines are the latency, the blue arrows are the latency, and the bars are throughput. And of course, because this is a Xilinx published number, the performance of FPGAs are much faster than whichever GPUs can get you. And also, latency is pretty good. Bear in mind, I think there could be many reasons for this particular chart. Sometimes GPUs are faster, sometimes FPGAs are faster, depending on the architecture of the neural network, a lot of reasons. But one of the reasons here could be because the batch size is 1. So latency is becoming more important when batch size is 1. The overhead of actually spawning a CUDA kernel becomes more important with a smaller batch size. So that could be one reason why FPGAs are doing so well in this particular chart. But the bottom line is FPGAs are pretty good. But how do you reach that kind of performance when typical FPGA clock speeds are much slower than CPUs and GPUs? Modern CPUs run at around 3 gigahertz, modern GPUs around 1.5, 2 gigahertz. CPUs vary by design, typically maybe 400, 500 megahertz. And we already saw kind of how FPGAs are so fast because of efficient fine-grained parallelism, also efficient coarse-grained parallelism. But before we jump into that topic, we have to talk a little bit about timing. And the pipeline design issues that we just talked about in a couple of slides ago is one hurdle that people coming from the software design aspect kind of have to first acclimate themselves to. That's part one. Part two, another thing that software designers, when they come into FPGA design, have difficulty acclimating themselves to is the issue of timing. Because now they have to think about propagation delay and clock speed on top of just implementing their logic. On top of implementing the logic, you have to think about how the pipelines and the data paths are constructed to get high performance. And on top of that, you also have to worry about the clock issues. So you kind of have to have a rule of thumb, back of the envelope knowledge of what kind of logic has high or low propagation delay, what is propagation delay, issue of logic depth, placement and routing, fan out, things like that. So I'm just going to go just a little bit into this topic, just enough to give you a taste. But for that, we have to go back into recapping propagation delay. In a clock synchronous sequential circuit, much like the CPUs that we dealt with in undergrad and grad level computer architecture, in a clock synchronous sequential circuit, the processing, which is the combinational part between the state elements, between the registers, must fit within a clock cycle. Combinational circuit logic has propagation delay, meaning it has to be less than the clock cycle because it takes time for electrons to move through the silicon. It takes time for the output of some silicon units to stabilize itself, et cetera, et cetera. We won't go into too much EE topics. If the propagation delay does not fit inside the clock cycle, either clock speed must be lowered, losing performance, or we have to modify it so that it now can fit inside the clock cycle. The question becomes, what kind of logic has high propagation delay? So yeah, here's a visual representation. And if we have some computation, multiplication, addition, whatever, from a bunch of state elements, and we store the results into the next state element, while the electrical signal moves through all of these things and they arrive here, so data starting out from here must arrive here before the next clock cycle can begin, because the data needs to be stabilized in this second state element so that whatever operation that depends on this value that starts on the next clock signal can be correctly done. And here, yeah. before we, and if there is a propagation delay that takes too long inside the circuit that you designed, too long meaning it's going to overshoot the clock that it's given, the synthesis tool will complain. And this is typically part of the synthesis report. And for example, Xilinx, it will create a file called post-route timing summary.report. I mean, you can always change the name, so the name itself is not important. The important part is there is a report. And if you look at it, if there is a timing violation, it's going to complain. There is a max delay path. This is a very, very long file. This is one part of this very, very long file. It's going to complain that there is a max delay path issue. There's a max delay path issue. There's a slack that's violated by 4 nanoseconds. 4 nanoseconds is about a little bit more than the clock width of a 200 megahertz block. So this violation is pretty severe. And yeah, it needs to fit inside the 200 megahertz clock of 4 nanoseconds, but the data path delay of this particular path is over 7 nanoseconds. So this is complaining that the numbers isn't being just directly subtracted because there's a lot of padding, there's a lot of margins going on, but it's complaining that there is a negative slack, which means there is a timing violation. And below, much like the example that I showed in the other set of slides, below, if you go down from here, it's going to show the critical path that caused this timing violation. But the bottom line is, starting from, let's see. I cropped it before we actually get there. Yeah, source, this is the important part. Source, it's starting from this state element, and destination ending at this state element is the critical path. So, and there's going to be a more detailed analysis of the critical path if you scroll down from here. So as designers, we have to look at this, where the signal starts from, where the signal ends up in, to figure out in BlueSpec nomenclature, where the critical path is, which rule the critical path is pretty much, because rules represent the combinational circuits. Yeah, which rule this error happens in, and we have to modify that rule to fix that problem. That's typically the approach that we take. And there's a couple of factors that result in this timing issues. The first and most prominent one is the logic depth. The most straightforward factor, which is the length of the critical path of the circuit. And for this, you have to kind of at least have a feeling for what kind of logic results in high propagation delays, because we need some insight to try to reorganize computation to remove the timing violation. The most straightforward case is simply just too much logic in a single cycle or a rule. Remember, if something that sometimes trips people up is that even if you have 100 lines inside a rule, if none of them have dependencies among each other, if they're all just parallel operations, then having a lot of stuff, lot of logic inside a single rule typically doesn't cause too much problems. The problem becomes if you have a piece of circuit that has results in a long critical path, if it has a lot of dependencies. For example, if you're doing a 16-dimensional Euclidean distance, you will have to do subtractions and then squares of 16 pairs of values. That's fine. Although subtraction and square is a pretty expensive thing to do, doing 16 of them in parallel isn't going to add too much more overhead compared to doing just one, because they can all be done in parallel. But if you add, one of the things you have to do after is you have to add these 16 things together. And even if you construct an adder tree, trying to add 16 things together within a single cycle is going to be kind of expensive. Or if you have many nested if-else statements, because these things create dependencies, that could be a cause of this. Also, multiplication is expensive compared to add and subtract. Division is really, really expensive, so there's that. One anecdote here, for FPGAs, the problem is kind of not as stringent, but if you look at CPUs, of course, even on CPU side, because the clock frequency has kind of decreased, kind of plateaued recently, it's not as stringent as it says here. But back in 2002, when we were dealing with single core and we were pushing clock frequencies to be faster and faster, the optimal logic depth per pipeline stage was supposed to have been 6 to 8 inverters. So 6 to 8 inverters is not enough to implement a 32-bit adder. That's how stringent this is. That's why back in the era of Pentium 4s and whatnot, we had really, really deep pipelines. But now it's kind of back to like, I don't know, 17 pipeline stages. But then we had CPUs with 50-stage pipelines because of these restrictions. Oh yeah, if you have nested if statements, that if statements typically are synthesized to, they actually manifest in the form of multiplexers, and multiplexers are kind of expensive in terms of logic depth. So there's that as well. Yes, that's where the problem of very large FIFOs also come in, because when you implement the FIFO, because you should be able to enqueue into a FIFO at any given cycle and get that same value out at the very next cycle if the FIFO is empty. In order to implement that semantics inside the circuit, the FIFO is implemented such that the input can be assigned to any of the slots, and the output can also come out from any of the slots. So if you have a 64-slot FIFO, then there needs to be a demultiplexer that can connect to any of these 64 FIFOs, and also a multiplexer that can come from any of these 64 FIFOs. And a very deep multiplexer like this one is kind of expensive to build in terms of both chip size, chip resources, and also logic depth. So if the latency is not a problem, consider what we can do is consider chaining multiple FIFOs via rules. So we can have the same number of slots, but across different FIFOs, smaller FIFOs, or use embedded block RAM, much larger, multiple kilobytes in order, implemented as a A6 shard using a size BRAM FIFO. So block RAM has hardwired addressing logic in a non-configurable silicon. So it's an efficient way to build memory units in the order of multiple kilobytes. Do we have time? I'm just going to go through 2 more slides and then we can wrap it up here. Yeah, that's the big overview. And just to go into a little bit of anecdotes and examples, some common pitfalls include variable length shift. Given bit 32B and S, computing this B shifted by S is very expensive because it has to implement a shifter logic, the one you see on the right, for every single benign looking statement like this one. Because 32 bits is 2 to the power of 5, we're going to have a 5-level shifter, which is kind of expensive. But interestingly, fixed length shift is pretty much free. If we do implement something like this, how this manifests in the circuit is pretty much just rewiring the circuits. So no latency, is just changing the names of some wires. Relabeling of wires, no delay. But this, if you change this to this very benign circuit turns into something like this. Instantiates a variable shifter, very large delay, and all of a sudden this could stop being tiny. Right. Similarly, another common pitfall is variable index access into vectors. If you have a vector and you do something like this, where IDX is a state variable, a register, this creates a tree of multiplexers like this one, because the value X that is being written to a vector 1 needs to be able to be assigned to any of these locations in the same clock cycle. So it creates a tree of multiplexers, very deep if vector is, or the index is very large. So this is also a common cause of timing errors as well. Another common pitfall is using modulo. If you do something like this, if you're counting and you say counter plus 1 modulo 32 is 0, this also involves a division operation, which is kind of expensive. So you can do something like this. If you can compare it against the value 32 without doing modulo and then reset the counter to 0. This will do the same thing, but it removes the requirement for a divisor. Also, if the comparison that we're doing is power of 2, then we can probably do something like a bit mask as well, like such. So this is I'm just throwing all these stuff out there, but these are kind of relatively advanced, moderately advanced stuff. So I don't think this will be completely necessary for the purpose of Lab 2, but just to give you a feel for the landscape, much like how we did with GPUs, these things are introduced. Okay, unfortunately, we have hit the time limit for today again. So I guess this will spill over a little bit into the next lecture again. So we'll talk about just a little bit more timing stuff, and then we can move on to neural network accelerators.